Howdy and welcome back to the CS128-Honors lesson video. In this video we'll be talking about Rust generics. But before we get to that, I want to talk about a couple of announcements, and specifically we're releasing a couple of important forms that we want you to fill out soon. The first one is the final group project matching form, which will be to match you with other people in the class to be in a group for the final project. Now, even if you already know who you're going to be working with, you'll have to fill that form out, so stay tuned to the announcements channel to fill that out. The other form, which we are going to be releasing tonight along with this lecture, is the midterm feedback form. And so here's the link. It will also be in the Discord announcement, and just make sure that you're filling that out so that we know how you feel as students in the course and can make adjustments as needed. So yeah, now with those announcements out of the way, let's get back to Rust generics. So, what is the motivation behind generics in Rust? Well, we have this main function here that's going to give us a pretty good example of why. So we're trying to get the biggest number from a list as well as the largest char from a list. And so for this system, we need to have two different functions, right? We have the largest integer, which takes in a slice of integers and returns an integer. And then we have the largest character function, which takes in a slice of characters and returns the largest character. Now you might notice on the left-hand side there that the code between the two is very similar, right? We have the same lines of the largest is equal to list 0 for item in list and so on, and they're the exact same code on the inside. The only difference is the types that we're using. And so this is obviously really inefficient, and let's talk about why. So yeah, these functions are functionally the same, and it leads to a lot of code duplication, right? Now, what that means is that, let's say the first function, we make a change to be for item in lists up until the halfway point in the list, right? Now we have to do that for every single time we have a different type for these functions, even though it's the same code on the inside. And what if we forget, right? Now we have undefined behavior because we might be dealing with one situation where one function is working as intended, but the next isn't because we had to copy paste code. So instead, we're going to be combining these functions for a generic implementation, which means that the code is going to be shared between the two, but will work with both. So Rust has generic types, which means that you can have this type T here instead. So instead of doing largest for integers and largest for characters, we can say we have this function largest, and it has some sort of associated type. So in this case, we're calling it T. And this type, which can actually be any type, is going to pass in a slice of that type, and then we are going to return the largest of that type. And so it's the same code as before, but now we are abstracting away which exact type that we're using. So then notice here that all these T's are now replacing any of those types. Now, of course, every time you try something the first time, 95% of the time it's going to fail. And so in this case, we get a compiler saying that the greater than sign cannot be applied to type T. And you might be saying, well, hey, why is that? Well, notice something that I said earlier, that T can be any type, right? We have not put any restrictions on it. So what if we had this really complex struct with like 15 different variables inside of it, and we needed to try and find the largest of those, right? Well, how do we determine which is the largest of that struct, right? If we just do greater than, it's not necessarily defined to actually work, right? Greater than is not defined for a struct that doesn't define it manually. So this is why Rust can't guarantee that we can use it with all types. And so here it's recommending that we use something called a trait to fix that, and we'll talk about traits in a minute. But before we do that, let's talk a little bit about generic types. And so you can see here we have another version of a generic type where we have a struct point that can take in a generic type. And so, for example, here we have x and y coordinates, and we're passing in for the first one a point that has a generic type of integers, and then a second point that has a generic type of floating points. And so notice they're using the same code for the same struct, but they are not the same types, right? We have floating points for one and ints for another, and it's totally fine. And if we tried to run this code, we're going to get 5 and 1, because we're not doing anything that is restricted to those types, right? We're not saying, oh, is this greater than something, right? Because we don't know what that type is for that struct, but because we're not doing anything like that, we're just printing out the values, that's totally fine. So let's talk a little bit about the performance implications of generics, and then we'll move on to traits. So in Rust, generics are type checked at compile time, which means that it pretends that a generic is a type that will work for all of the different things that you tell it to work for, and we'll see if there are any issues. And what this means is that there's no runtime performance penalty. Once you compile the code, it is going to work 100% as quickly as if you had manually written that generic type, but it's obviously going to be more readable to you and other humans. And so the way that Rust is doing this is it's generating the code manually for each of those types as if it were doing your job, but it only does the ones that you need. So let's say you're only using this generic struct with an associated type of ints, right? It won't create one for characters. It won't create one for floats, right? It will only do what you need it to do, and it will do it super quickly at compile time so that you don't have to worry about it. And so this way it's very fast. It's just as if you had written it, but it's making it less likely that you're going to make a mistake revolving around that associated type. And so this is actually similar to how C++ uses templates, which are similar to generics, except that's the C++ version of them. So let's talk about traits. So traits in Rust are similar to Java interfaces, which you should remember from CS124, 125, or a proficiency exam from when you took, say, AP Computer Science in high school. Now, Java interfaces are allowing you, and as well as Rust traits, are allowing you to provide a layer of abstraction between the actual implementation of a function and the area where that function is being called, right? So you can have an array of a bunch of different things that all conform to the same trait, and then iterate that over that array even though they might be different types. And so this allows you to have a bunch of generics while guaranteeing that you're able to perform certain actions, say make sure that they're all equal, right? And so let's take a look at how that looks in code. So the first few lines there is the example of declaring a trait. So in this case, we're creating a trait, and don't worry about the pub. Pub is just the scoping. So we could just have trait summary, and then inside there we have a function called summarize. And summarize takes in a struct of some sort and then returns a string with that function being called. So now here's the important part about the summary trait then, right? Summary can apply to any object, any struct, as long as we write the code that will summarize a struct. So for example, we have this news article struct, right? And it has a headline, a location, the author, what kind of content it is, and all of that kind of stuff. And so now we have this implementation block where we're saying implement the summary trait for this news article, right? So now instead of just implement news article and then putting some sort of function in there, we're saying summary for, which is telling Rust, hey, this now is going to conform to this trait. And so as you can see here, we are defining the summarize function to just take in the news article and then give the headline, author, and location, and just print it back out. And so this is a way to declare a trait and then to make sure that a struct conforms to that trait. Now, we can also provide default implementation for a trait. So for example, what if we want to make sure that traits are able to be used even if we haven't manually provided implementation for something? Well, we can give a default implementation. In this case, we're just saying read more, and then you can find out the summary from there. But this way, any struct can be of trait summarize or of trait summary and still work. It just will give this default implementation instead. Now, the next part here is a function that we are now using a trait on. So now we're saying we have this function called notify, and it will notify the user of this weird command line application of a generic type where that type can be summarized, right? In this case, it's a trait, it has the trait summary. And so we're taking in that item that can be summarized, and then we're printing out breaking news and then summarizing it, right? And so this is the idea that we needed from before, where we have this trait which restricts what types we can use, right? Now, theoretically, with this implementation of summary that we have at the top there, that wouldn't apply because, say, if we passed it an int, it would just say read more. But in theory, if you didn't do that, this way you can have type checking and not have to worry about those kinds of issues. And then finally, at the bottom there, we have another version of notify, But now what we're doing is instead of just saying we need the summary trait, we're also saying we need the display trait. And so the display trait could be declared somewhere else, but let's say it prints out the actual content of the article. So that display trait also needs to be used in order for us to be able to notify the user. And so finally we have another function. In this case, we're just using generic types for our type signature. And we're saying t and u. And instead of having to put that in the function signature like we had before, we're putting it on a separate line using the where syntax. So after the return value, but before the opening bracket, we're using where, and then we're saying t:, and then whichever traits it needs to conform to, and then the same for u and any other generic types if we had more for this function. And so all of this gets boiled down into that line above at compile time, but that way we don't have to worry about it looking as long, because this could be like 150 characters if we weren't careful enough and put it all on the same line. And this makes it a much more readable function signature, and we're able to see what generics need which traits. And then finally, down at the bottom there, we have a function called return summarizable, which will return a object or a struct of some sort that is of trait summary, right? Now, one important thing to note with that is that you can return any struct that implements the summary trait, but that function, return summarizable, must only return one type. So you can't, let's say, have a news article and a TV article and then have those both be returned from return summarizable. You can either return all news articles or all TV news, right? You can't do both. And so that is really important, because if you're not careful, you might mess that up and then you'll get yelled at by the Rust compiler. So let's go back to our Rust generic types example. So now we have the largest t function just like before, but now inside our first part here, we're going to say t must conform to the trait partial ordered and copy. So partial ordered is basically saying that it must be partially orderable, which means that they must be able to be ordered between less than, greater than, or equal to, right? And that's why it's partial as opposed to full, is that it can be equal to as opposed to a definitive order of this one is greater than or less than. And then the copy trait is saying that we are allowed to copy these values directly from a list or a slice or something else like that without taking the reference to it. And that makes it memory safe, like we talked about earlier with ownership. And so that copy trait means that we can now take items from those slices and not have to worry about the references and everything else. And so if we run that code with the main function that we wrote before, but now just using largest instead of like largest char and largest int, we'll now get the largest number is 100 and the largest character is y, just like we'd expect. So yeah, that was Rust generics. I hope you enjoyed, and I'll see you in the next week's lesson video.